Okay, good morning everyone. So welcome to the Year 10 chemistry class in Elite Medics. Today we're going to be looking at atmospheres, fuels, atmospheric pollutants and global warming. For those of you that don't know me, my name is Ravi. I'm a fourth year medical student at UCL. I've been teaching the Elite Medics for about 3 years now, and I've helped many of you try and do as well as you can in your exams. The aim here is to try and get you ahead of your classmates, and to try and give you the best possible resources that you can achieve the 8 or 9 in your GCSE exams. Now, what are we going to be doing today? So those of you that are familiar with the way this class runs is you would hopefully have been given a question pack with loads of past paper questions, and I've integrated them into this PowerPoint, and we're going to be having a look at a few of them today, and I'll be showing you the mark scheme answers as well as my approach to answering these kind of questions. And we're going to supplement that with the relevant theory. So I will try to teach theory first, and then I will go through some past paper questions with you. I like to keep things interactive. As you can see here, I've got my main dashboard. This is where I can see all the questions coming in. So do ask me any questions. I also have 2 fantastic moderators in the back end who will be helping me to answer any of your questions. If you have any questions directly to me, then just put them down below, and hopefully the moderators will leave it for me to check. I'll check the chat every 5 minutes or so. Also, I would say that you don't need to spend too much time making notes, just worry about paying attention, and you will get a copy of this PowerPoint and the recording at the end of the lesson, as well as a copy of the mark schemes as well. And finally, there will be a feedback form coming throughout the lesson, so if you could just fill that whenever you get a chance, that would be great. Okay, so without further ado, let's make a start. So this entire topic today is about green chemistry. So we're looking at the different atmospheres, how the Earth came about, what gases were introduced at different parts of Earth's life. And then we look at the different pollutants that arise, especially from burning different fuels. And that's how we'll introduce the hydrocarbons topic. And finally, when we release these atmospheric pollutants, it can lead to what we call global warming and climate change. Okay, so we're kind of going in sequence, so we're going to introduce each new thing as it comes along. Okay. So we're going to start with the Earth's atmosphere, then we're going to go to hydrocarbons as fuels, then atmospheric pollutants, and finally the greenhouse effect. Now, as you know, I like to keep things interactive, not just through the chat, but also we've got 2 Slido quizzes that I've prepared for you. One is slightly longer, it's the first one, and the second one will be slightly shorter, and that'll be after lunch. Okay. And I will flash up the Slido code when the appropriate time arises. Okay, so what do we need to know about the Earth's atmosphere? So our learning objective is to know the current composition of the atmosphere, and then we want to compare this to the Earth's early atmosphere. And you need to understand why it was, what the composition was, and why it was. You want to understand the evidence for the Earth's early atmosphere and why it is limited, and understand how volcanic activity, oceans, the evolution of plants, all affected the carbon dioxide and oxygen levels in the atmosphere. Okay. Especially this one is a typical question that comes up 3-4 markers, so you want to definitely have that unlock. You can see we've got these learning objectives from your different various exam boards. So AQA, again, we're looking at the composition of gases in the atmosphere, and then looking at the Earth's early atmosphere, how oxygen increased, how carbon dioxide decreased, so we need to know all these processes. OCR is looking at the evidence for how the atmosphere was originally formed, then how an oxygen-rich atmosphere was developed over time, and then describing the greenhouse effect. Edexcel, again, very similar things, looking at gases produced by volcanic activity, the Earth's early atmosphere due to that was thought to contain little or no oxygen, large amounts of CO2, water vapor, and small amounts of other gases, and you need to know the evidence. So notice how a lot of them are talking about interpreting the evidence. You want to explain the condensation of water vapor forming oceans, how carbon dioxide levels decreased, and the growth of primitive plants, primitive meaning the first plants that kind of colonized the earth, how they use carbon dioxide and released oxygen by photosynthesis. Okay. And note, we want to be able to describe the composition of today's atmosphere. So you can see that across the board, regardless what exam board you're doing, it's very similar content that you need to know. And this is not limited to just AQA, OCR, and Edexcel. This is also for WJEC, Cambridge GCSE, etc. So let's look at the Earth's atmosphere as we know it today. So firstly, what is an atmosphere? Atmosphere is the layer of gases that surrounds a planet. And our Earth's atmosphere provides life with oxygen. It helps to keep the planet warm due to our greenhouse gases, and it protects from the sun's radiation. And this is what we call our ozone layer. So the ozone layer kind of absorbs UV light as it enters from the sun as it enters Earth. Okay, we'll talk about that in a minute. So if we look at the composition of the gases, paradoxically, you see that nitrogen has the highest composition, 78%, where you might think that majority of the air we breathe is oxygen, but actually it's nitrogen. Okay, 21% is oxygen, 0.9% is argon, and 0.1% is other gases. Okay, so the two biggies are nitrogen, which is 80, and oxygen, which is about 20. Okay, so you can approximate it to 80 and 20. All right. Very important. This actually came up as a multiple choice. I think this is the first question on my GCSE paper back in 2016. Okay, the ozone. So what is the ozone? It's the layer that protects the planet from the sun's radiation. So it's made out of O3, which is our ozone, and it's formed due to our ultraviolet light. Now, what happens is UV light will go and break down oxygen molecules into oxygen radicals. Okay, so this is a photodissociation reaction. Photodissociation. So we're using light energy to break apart a molecule, okay, and it's turning it into two oxygen radicals. Why do we say they're oxygen radicals? Because they have electrons that are unpaired, right? Oxygen is stable as a diatomic, right? We always say that these gases are such as oxygen, bromine, iodine, chlorine, nitrogen, they are all more stable when they're diatomic, they buddy up. But when you split it with light, then it splits apart, and now all of a sudden each oxygen is now unstable because it doesn't have a full outer shell. Hence we call it an oxygen radical. Okay, so we'll say this is a oxygen radical. Okay, and then this oxygen radical will then react with more oxygen to then make ozone. So this is the formation of ozone. Okay. Now, when UV hits the ozone, it absorbs it and breaks it down. So you get the formation of ozone, and you can also get the breakdown of ozone. So you get some sort of reversible reaction. So the ozone prevents the UV from reaching Earth. Okay, so ozone plus UV will make oxygen radical and O2. Okay, you can see it's basically the reverse of this. So you know that this formation of ozone is a reversible reaction. Okay, it can both make ozone and ozone can be broken down. Very important, you know that it's the UV light. And where do we get the UV rays? The UV rays come from the sun. Okay. In terms of memorizing equations, I would only try to memorize this equation here and this one here. This is the same, it's just the reverse. Okay, just remember that this equation is the same as this one, but you're just adding UV light. Yeah. Okay. Any questions on the ozone? Well, I think we had a few extra people join, so welcome to anyone that's just joined. We're currently looking at the Earth's atmosphere, and we're looking at the ozone layer. Right, so we know about the ozone layer and how it acts as protection from the sun's UV rays. What was the early atmosphere of the Earth? So the Earth formed 4.6 billion years ago. Okay, that's a long time ago. And it was from gas and dust that was left over from the formation of the sun. So the gas and dust kind of joined together and helped make the Earth. And the Earth was formed by the accretion of planetoids. And at this point, the atmosphere was mainly hydrogen and helium, okay? And there weren't any other gases. So this atmosphere was then lost as Earth's gravity was too weak. It was blown away by the solar wind, and you got a collision with a large planetoid, which was then knocked away, and thus formed the moon. Okay. So the early atmosphere didn't survive very long. Key points to note from this is that the main gases were hydrogen and helium. There wasn't any oxygen, no carbon dioxide, no nitrogen, none of the main gases that we know today. Then we have atmosphere 2. This is where things got very hot. This is where volcanoes erupted, and the eruption of volcanoes released CO2, sulfur dioxide, and water vapor. Because of this volcanic activity, this is what allowed the atmosphere to form, with water being majority of substances in the air, 80%, then carbon dioxide being 10%, and then other gases making up 10%. Notice we still don't have any oxygen yet. Okay, so that's the big point here. There's no oxygen in atmosphere 2. We have all these other gases: sulfur dioxide, carbon monoxide being toxic, hydrochloric acid, hydrogen sulfide, methane, and ammonia. Okay. Right, so but remember, this is mainly due to volcanic activity. Then we have oceans starting to form, and this was about 3.8 billion years ago. We had the Earth cooling and temperature lowered below 100 degrees C. We know the 100 degrees C is the boiling point of water. So if we go below 100 degrees C, water will condense and thus form the oceans. And this is where things become very interesting, because oceans are a very big carbon sink. Carbon sink. You want to know this key term. So what is a carbon sink? A carbon sink is something that can actually store carbon. Yeah. We have lots of examples. We have the oceans, we have our lakes, any body of water can store carbon. We also have things like peat bogs, which are peat bogs are just they're a store of carbon. I'll explain it. I'll try and get a picture up in a bit. You've also got things like fossils that can also store carbon in them. Okay. But by far our largest carbon sinks are our oceans, because it's a large body of water and CO2 dissolves inside them. Okay. Then it precipitates, forming carbonates, and this is where we get calcium carbonate, which is our limestone. And you'll know that a lot of the cliffs, I think famously the cliffs of Dover, are made of calcium carbonate, limestone. They call it the White Cliffs of Dover. So how does that happen? So we have water reacting with the CO2. So CO2 dissolves in the oceans, making carbonic acid, and then the carbonic acid will precipitate on the silicate rock. So you'll get the rocks, the cliffs, and this will precipitate on it. Hence, you get a layer of calcium carbonate on it, and you'll get your calcium carbonate, and then it will release the silicon dioxide and water. So now you have these nice calcium carbonate cliffs. Okay. So that's the key thing. Oceans being carbon sink due to the fact that the Earth cooled down lower than 100 degrees C. Water condensed, formed these oceans into which CO2 dissolved and thus precipitated, forming our carbonates. Now, at this point, we were able to get a tiny amount of oxygen, and this is formed due to the splitting of water molecules. Note, we're looking at UV rays again. So UV rays hit the water and break it down into hydrogen and hydroxide. And then we have CO2, which is a gas that is broken down by the UV rays into carbon monoxide and oxygen. And thus we have oxygen reacting with hydroxide to give oxygen and hydrogen. Okay, so you may think that you get some toxic gases, but in the end, everything kind of balances out and we get oxygen, hydrogen, and a very small amount of carbon monoxide. Okay. So note that it's not majority, only a tiny amount of oxygen is formed here. You'll see where the majority of the oxygen comes from, but you just need to remember that the oceans, the key role they had was for dissolving CO2 and precipitating to form carbonates. So atmosphere 3, which is about 3.5 billion years ago. So this is 1.1 billion years ago, after the first Earth's atmosphere. Okay, so 3.5 billion years ago, life evolved, and soon, 0.1 billion years later, life was able to photosynthesize. So what was this life that evolved? Usually it was mainly algae, photosynthesizing plants that were able to do so. And once you had loads of these plants, they were then able to photosynthesize and thus release oxygen. And it makes sense because, do you remember, with all that volcanic activity, there was a lot of CO2 about. Now, yes, a lot of CO2 did dissolve in the water, in oceans, to form carbonic acid and then precipitate, but there is still a lot of CO2 kicking about in the air that would be taken in by plants in our photosynthesis reaction as we know it today. Yeah, CO2 plus H2O makes C6H12O6, which is glucose, plus oxygen. Now, we're not doing a chemistry lesson, but ideally we should balance this stuff. So we've got 6 CO2 because 6 carbons here. Then there's 12 hydrogens, so we need 12 hydrogens here, so 6 H2O. And finally, we have 12 oxygens plus 6 oxygens, that's 18 oxygens. There's 6 here, so you need another 12, so therefore 6 O2. Yeah, so the way I like to remember is 6, 6, and 6. Yeah. At first, the oxygen that was then released by these plants then reacted with rocks to make metal oxides, and then the oxygen entered the atmosphere. Okay, so most of the oxygen at first reacted with rocks, but any excess oxygen was then entered into the atmosphere. Okay. Any questions? Is this topic also part of using resources? I think so, because using resources is green chemistry. And I think maybe you're talking about using fuels, so yes, I think it might be. If the carbon dioxide dissolved into water precipitated carbonates, would this make the water milky white? So yeah, essentially you'll get the oceans wouldn't be pure water because it would precipitate, and you would get this cloudy water, basically. Yes. Okay. So let's have a look at a graph showing this. So until about 2.5 years ago, you wouldn't have much oxygen in the atmosphere or in the oceans. Then you've got the first life coming about, and then the oxygen would be absorbed by oceans, rocks, and lands. Yeah, because they will, the photosynthesizing life will then give out oxygen, and that will be absorbed by oceans, rocks, and land. Any excess will then be in the atmosphere, and you can see that you're over time you're getting your first eukaryotes. Remember, eukaryote is a multicellular organism. But I suppose that the first eukaryotes initially started out as prokaryotes and then adapted and evolved. Then you have multicellular eukaryotes, and then to about 0.8 billion years ago, you start to get your marine life and then your land plants as well. And this is where your oxygen accumulates in the atmosphere. When oxygen is absorbed by oceans, rocks, and land, it's not likely that you're going to have much life that is metabolically active, right? We know that metabolically active animals, so us, all our sea creatures, they require a lot of oxygen. If there's not much oxygen in the atmosphere, if the oxygen is trapped in rocks, land, oceans, then they're not going to be able to survive. So it's only in the past 0.8 billion years ago that there is sufficient oxygen in the atmosphere for metabolically active eukaryotes to actually thrive. Okay. So as long as you have a general picture of the timescale and you kind of have an idea in your head of what's happening, that's all you need. You're not going to be expected to recreate this graph. They may ask you to interpret this graph perhaps and give reasons as to why this happened. So you could say that between 3.8 billion years and 2.5 billion years, there was no oxygen in the atmosphere or oceans, largely due to the fact that majority of the CO2 was in the oceans, and there wasn't much photosynthesizing life that was able to then create oxygen. And even when there was oxygen being produced by algae, for example, a lot of it was trapped in oceans, rocks, and land. So only when they were saturated with oxygen does oxygen then accumulate in the atmosphere. Okay. So just to add on to this, so plants and marine life did more than add oxygen to the atmosphere. They also removed CO2. So they're now changing the composition completely. Instead of having the atmosphere atmosphere 2, where there was lots of CO2 from the volcanic activity, now not only does algae produce and other marine and plant life, not only do they produce your O2, but they're now removing CO2. So plants did this with photosynthesis, as we've seen, but now marine animals, they made carbonate shells out of carbon dioxide. Okay. When these animals then died, the carbon became trapped as rock, hence the limestone. Okay. Because of all this, CO2 in the atmosphere decreased. It decreased so much that we had an ice age. Now, volcanoes continued to erupt. The volcanoes didn't stop erupting, and they kept erupting, putting more CO2 into the atmosphere, allowing the Earth to warm. Okay, so this ice age that happened due to the reduction in CO2 was then reversed as volcanoes continued to erupt, and thus the Earth was able to warm up again. So a quick comparison of the different gases in each atmosphere. So atmosphere 1, we have our hydrogen and helium. In atmosphere 2, we have water, carbon dioxide, and as majority being water, and then your other gases. And then in atmosphere 3, which is our atmosphere today, we have majority nitrogen, oxygen, and then our other gases are argon, carbon dioxide, water vapor, and methane. Okay. Any questions on any of that so far? I think we're getting the hang of it. It's not much to really understand. It's just a lot of facts to remember. And I wouldn't worry too much about knowing all the exact timelines. Just know roughly the early atmosphere, like the earliest atmosphere 4.6 billion years ago, then the second one, and now our present day atmosphere. And you just need to know the features of each one. Okay, so to summarize, In present day, Earth's atmosphere is 21% oxygen and 78% nitrogen. Atmosphere 1 is entirely hydrogen and helium, and that was blown away. Atmosphere 2 had 80% water vapor and 10% carbon dioxide. Again, due to the volcanic activity. Then the Earth cooled and oceans formed, and plants started to photosynthesize. So we got that 80% water vapor being our like steam basically, that would then condense to form water and thus oceans, and plants started to photosynthesize. This made oxygen and first reacted with rocks, then it entered the atmosphere. It used up the carbon dioxide, it took in the carbon dioxide, and it made calcium carbonate. So, for example, the rocky cliffs, as well as shells from marine animals. And oxygen levels slowly rose over time as more and more plants photosynthesized, and carbon dioxide levels decreased as plants photosynthesized, and as marine animals used carbon dioxide for their shells. Okay, any questions? Let's have a look at, thank you to the moderator for the notes. So let's have a look at some exam questions. So these exam questions are really good. They're kind of typical questions that you'd get in your exam. So if we look at this first one, the Earth has a layered structure and is surrounded by an atmosphere. So here's our atmosphere. Then we've got the crust, the mantle, and then finally the Earth's core. Scientists believe that the Earth's atmosphere is formed by volcanoes releasing gases. This early atmosphere was about 95% carbon dioxide. So this wasn't the first one, but this was the second Earth's atmosphere. The Earth's atmosphere, the composition of the Earth's atmosphere is always changing. The Earth's atmosphere today contains about 0.035% carbon dioxide. So what happened to most of the carbon dioxide that was in the Earth's early atmosphere? Well, you could say that the CO2 was stored in oceans. It was taken up by photosynthesizing plants that would then take in CO2, give out oxygen. You could say that marine life used the CO2 to make shells, precipitating into calcium carbonate, and it also made our calcium carbonate rocks that are found still to this day. Yeah. So you've got used by plants for photosynthesis, absorbed or dissolved in oceans, and locked up in fossil fuels, limestone, and our sedimentary rocks that are still seen today. About 60 million years ago, a large meteorite hit the Earth. This meteorite heated limestone in the Earth's crust, causing the release of large amounts of carbon dioxide. Explain how carbon dioxide is released from limestone. For this, you just need to know limestone is calcium carbonate, CaCO3, and that this is a solid. When it's broken down, it forms calcium oxide plus CO2. Okay, this is a solid, this is a gas. Okay, so this is what we call our thermal decomposition reaction. You've heard me mention this several times in previous lessons, thermal decomposition. Okay, so you can put this into words or show an equation. So calcium carbonate is thermally decomposed into calcium oxide CO2. Note how just writing this equation up here gets you 2 marks. Yeah, so it's useful to know these little tricks of what they're getting at, and if you can just make your life easier for yourself, you can just write this out for 2 marks. But obviously you have to get it right. If you get the wrong equation, then obviously you won't get the mark. Okay, the graph shows the percentage of carbon dioxide in the Earth's atmosphere over the last 50 years. Explain as fully as you can why we should be concerned about the information displayed on this graph. So it looks like the percentage of CO2 in the Earth's atmosphere has been steadily rising, pretty much in a linear fashion since 1960. So it just goes to show that our CO2 levels are going to continue rising in the future. maybe actually it's not even linear. Probably it's getting a bit steeper, maybe. Yeah, it's getting steeper because it was a bit shallow. If it was the same steepness at all times, then it would probably go through this point here. But it starts off a bit shallower, and now it's getting a bit steeper. I can see it, especially in the last 20 years with all these man-made processes. A lot more of burning fossil fuels, a lot more of deforestation for building houses and settlements. That's going to easily increase CO2. Okay, so increasing CO2, more rapid increase recently. So yeah, more rapid increase recently, and this CO2 will cause global warming. Okay. Then you can talk about how that is climate change or causes sea level to rise or ice caps to melt. Okay. Note they say do not accept the ozone layer because it's got nothing to do with the ozone layer, because remember ozone is only due to oxygen and UV oxygen radicals and UV light. Now there are some substances, namely chlorofluoromethanes, and you can get chloromethanes. All of these tend to, if released into the air, they tend to react with ozone because they form these radicals which then break down the ozone. Okay, and which is bad, so you don't want to do that. But that's got nothing to do. You'll learn that in A level. Okay, we're happy with that. Check if there's any. Can you show us a diagram of how and what the volcanoes did what they did? Okay, I'll try and find one later, but essentially the volcanoes literally just, if you think about it, when the volcanoes erupt, alongside all the lava, you're going to get spitting of your lava, plus all these gases coming out of the volcano, such as sulfur dioxide, carbon dioxide, carbon monoxide, lots of these atmospheric pollutants. But you also get things like your water vapor, you get things like your CO2, all of these gases that we know today. Scientists believe that all the continents of the Earth were once joined together. The huge supercontinent was called Pangaea, or Pangaea. So this is something that you may have learned in geography, actually. And this was 200 million years ago, and this is today. So this is the continents we know today. In 1915, Alfred Wegener had an idea that the change shown in the diagram was caused by continental drift. Most scientists could not accept his idea. Suggest why most scientists in 1915 could not accept Wegener's idea of continental drift. Well, most likely, whenever we don't support a scientist's idea, it's probably due to lack of evidence. So if there's any other, so other scientists had either other views that were contradicting, maybe, or maybe people didn't respect Wegener as a scientist. They just thought he's a nobody who's just putting out a theory. Yeah, but the main one I would say is that the fact that he had no evidence or limited evidence. Okay, so use this information and your knowledge and understanding to explain how continents move. Okay, so this one's a bit of a tricky question. You wouldn't know this just from chemistry, but the plates move. The heat energy causes convection currents in the mantle, and that's what thus causes the continents to move around. Okay, it's not really chemistry, it's a bit of a tricky question, this. Okay, are we happy with that? No worries, we've just been looking at the Earth's atmosphere to start off with, so we're on the exam questions now for this, but we'll be recapping the Earth's atmosphere in the Slido quiz that I've got later on. Scientists study the atmosphere on planets and moons in the solar system to understand how the Earth's atmosphere has changed. So let's look at this. Millions of years ago, the Earth's atmosphere is probably just like that of Mars today. The table shows data about the atmosphere of Mars and Earth today. So Mars today, Earth today. Okay, direct comparison. The percentages of some gases in the Earth's atmosphere a million years ago have changed to percentages in the Earth's atmosphere today. For two of these gases, describe how the percentages have changed and suggest what caused this change. Okay, so Earth's atmosphere a million years ago is likely to be the same as Mars. Okay, that's what they said. So you're comparing this to this. So we're saying that nitrogen has gone up, oxygen has gone up significantly, water has pretty much stayed the same, carbon dioxide has reduced significantly. So you can talk about, so I'm sure there's lots of points here, so let's go through each one. So nitrogen, you get the bacteria that they're called nitrifying bacteria or nitrogen fixing bacteria, and they essentially introduce nitrogen into the atmosphere. Oxygen, due to photosynthesizing plants releasing oxygen into the atmosphere. Water stays the same, and CO2, again, you could talk about photosynthesis, or you could also talk about marine life, using it for the using CO2, precipitating calcium carbonate for the shells, or just in general, the oceans dissolve the CO2, forms your carbonic acid, which precipitates into your calcium carbonate rock, which is sedimentary rock that still stands today. So yeah, we've talked about all of this. Locked up in sedimentary rock, dissolved in oceans. Oxygen is increased due to plants, bacteria, microorganisms, vegetation, trees, photosynthesis. Nitrogen increased due to bacteria, and oh, this is a good one. Ammonia reacting with oxygen. That's what I had left out. So ammonia reacts with oxygen to make nitrogen, because ammonia, as you know, is NH3. Let me see if I can work out what the equation is that would form that. I believe it should be, if it's making nitrogen, it should also make water. And if we balance this, I reckon you could probably do 3, 2, 6 hydrogens, 2 nitrogens, 3 oxygens. So we'll just make this 3/2, and you could probably double everything if you wanted to. But yeah, so ammonia reacts with oxygen, making nitrogen. Okay. And where did that ammonia come from? If you remember, the ammonia came from that atmosphere 2. When the volcanoes erupted, they released ammonia as well. Titan is the largest moon of the planet Saturn. Titan has an atmosphere that contains mainly nitrogen. Methane is the other main gas. When it rains on Titan, it rains methane. That's what it's saying. Use the information above and your knowledge and understanding to explain why. So for this, they've given us some boiling points here. And the average surface temperature is minus 178. Let me have a think about this. So it's saying when it rains on Titan, it rains methane. So this is a liquid. Why is it a liquid? Because the average surface temperature is minus 178. And the boiling point is minus 164. Now for that, you need to realize that minus 164 is up here, minus 178 is down here. Now, I know this seems very easy, like why am I saying that? But because if this is minus 164 and this is minus 178, and the boiling point is at minus 164, it hasn't quite reached the boiling point yet. Yeah, so therefore it's still a liquid. Now, if you don't do something like this in your head, it can be very difficult to figure out which is the higher number. Technically, 178 looks bigger, but because it's negative, this is actually the lower number. Yeah. So yeah, it hasn't reached its boiling point, which is -164, therefore it's still a liquid. Yeah. Okay. Ultraviolet radiation from the sun produces simple alkenes such as ethene and propene from methane in Titan's atmosphere. State the general formula for alkenes. This is something we're going to look at in the next portion of the lesson, but this is general formula it says. So the general formula is going to be CnH2n. Okay. Yep, CnH2n. Okay. Great. So that's the Earth's atmosphere done. Hopefully we're happy with these learning objectives. We know the current composition of the atmosphere. We've described the Earth's early atmosphere. We understand the evidence for the Earth's early atmosphere and why it's limited. We understand how volcanic activity, oceans, the evolution of plants affected the carbon dioxide and oxygen level in the atmosphere. Okay, so hopefully you can tick these all off. Right, it's 10:40. Let's take a quick break before we move on to the second part of the lesson. So quick 5-minute break. I'll see you guys at 10:46. All right. Drop any questions that you may have down below. All right. All right, take care. See you. All right. Okay, so welcome back. Hopefully you had a good 5-minute break. So we're going to move on to hydrocarbons as fuels now. So what do we need to know? There's a lot we need to know. So we want to know that crude oil is the main source of hydrocarbons and is a fossil fuel. We want to know the difference between alkenes and alkanes. We want to understand the process of fractional distillation and that crude oil is separated into fractions. The properties of different fractions depend on the size of the hydrocarbons it contains. And then we want to know about the different properties based on the length of the fractions. Know the uses for hydrocarbons of different lengths. Know the process of cracking and why it's done. Know the products of hydrocarbons when they combust in excess oxygen. Understand when incomplete combustion occurs and know that carbon monoxide is a toxic gas. Okay. I'm not going to read all this out, but you can have a look at this in your own time. In the same way as earlier, learning objectives are taken from the exam board spec points. Yeah. Same here. We need to know these key terms: and boiling points, viscosity, flammability. Cracking is all here. Similarly in OCR, knowing general formulae of alkanes, alkenes, describing cracking. And again in Edexcel, knowing the different fractions, what they're used for. This is a highlight. This is just a memory game here, just memorizing what the uses are of each fuel. Okay, explain why cracking is necessary. Fine, we're happy with that. All right, now on to the actual theory. So hydrocarbons, the clues in the name, made from hydrogen and carbon. And that's it, only hydrogen and carbon. Now, alkanes have a general formula, which is CnH2n plus 2. What does this mean? It means that the N could be any number. So if I make this 1, the number of hydrogens is going to be 2 times 1, which is 2, plus 2 is 4. Okay. This example here, propane, we've got 3. So 3 times 2 is 6, plus 2 is 8. Hence C3H8. Okay. We can display it like this. So this is what we call the displayed formula for anyone that hasn't actually looked at this stuff in chemistry. So displayed formula. And since there are no carbon-carbon double bonds, we call this saturated. Okay, because it's complete. Each carbon is fully saturated in hydrogens. Okay. We can compare this to alkenes, which again are a type of hydrocarbon. They have a different general formula, CnH2n. Thus, if I have 1 carbon, I have 2 hydrogens. If I have, there isn't actually an alkene with 1 carbon. The smallest alkene, this is something you want to know, smallest alkene, smallest alkene equals C2H4. Okay, the reason for that is you need a double bond, right? And you can't have a double bond between 1 carbon, right? So propene is C3H6, butene is C4H8, and so on. Okay. We call these unsaturated because there's the presence of a double bond, and we know that carbon has a valency of 4. What does that mean? It means that each carbon atom can bond with 4 other atoms. Okay, so because carbon has a double bond, it now no longer is able to bond to 1 extra hydrogen. Compare that to this here. We had a hydrogen, we lose this hydrogen, and on this carbon as well, we lose the hydrogen and they become a double bond. Yeah. So we say it's unsaturated because it doesn't have, it's not fully saturated in hydrogens. Okay. So alkane versus alkene. Alkenes are used to make polymers, so plastics, and alkenes are more reactive than alkanes. Now, why are alkenes more reactive than alkanes? So I don't want to make this too much of a chemistry lesson, but I know all of you will be doing chemistry because it's GCSE. So I'll explain it to you anyway. The reason why alkenes are more reactive than alkanes is if you take an alkene, let's just take ethene, for example. Okay, ethene looks like this. This double bond here actually looks like this, okay? What happens is you get, so you've got a sigma bond on the inside, and then you also have this overlapping of what we call p orbitals. So don't worry too much about that. But what we have is we have this pi bond either side. So the sigma bond and the pi bond, okay? Now, essentially, all this is saying is that now there's a region of high electron density, okay? And when there is a region of high electron density, it means that it's able to attract what we call electrophiles, things that love negative charge. And because of that, they're more reactive. Yeah. If we take an alkane, for example, so we just take ethane. These electrons, do you know the electrons between these two carbons? If you think about a dot and cross diagram, they're sharing electrons, aren't they? Yeah, there's a shared pair of electrons. I'm not doing the whole thing, but you realize that this covalent bond is just a shared pair of electrons. So because they're fixed in this bond, the electrons are not free to spread around. So yes, in this in an alkene, yes, electrons are stored in this bond, but also you get electrons in this cloud here and here. Okay, that's what gives it a region of high electron density, which is able to attract other substances that are positively charged. They get attracted to this region of negative charge and hence react. Yeah, so this is the reason why. Now, this is an A-level explanation. You're not expected to know this at GCSE, but I just always like to understand things from first principles. So if you're like me, this is the reason why. If you don't want to, if it's too complicated, leave it and just remember alkenes are more reactive than alkanes. But it's, or in simple terms, double bond makes it more reactive. Okay, that's it. Now, the test for bromine water, sorry, the test for alkene, so the test for unsaturation essentially, is adding bromine water. If there is no change, right? If the bromine water stays orange, then the alkane is present. If, however, the bromine water turns colorless, then alkene is present. So let's look at this. What happens? Why does that happen? Okay, again, this is going to be an A-level explanation, but I want to do this because we've got ample time for this lesson, and I want to solidify understanding over just cramming and memorizing things. Okay, so alkene plus bromine makes bromoalkene. Sorry, no, it's not. Bromoalkane. It's wrong. Bromoalkane. Okay. Now, if we take this alkene plus this bromine, what actually happens? Why does it turn colorless? Because the bromine is no longer in solution. But let's actually see what happens in terms of the carbon-carbon double bond breaks. So we're going to look at this bromination of an alkene. So we're using ethene. So let's take our ethene. Okay. Right. And we have our bromine molecule that comes towards it. Okay, that's reacting, that's going to react with the alkene. Okay, so what's going on here? Well, because like I said, do you remember I said that this double bond has a high region of electron density? Yeah, it's a region of high electron density. Therefore, it's going to be very negatively charged. Yeah. What this does is any molecule, would you agree that bromine molecule is not charged, right? We've talked about this your year 10 chemistry. Yeah, so we've talked about this, that in a previous lesson we've said that things like to be stable, right? So bromine with bromine is stable. It has no overall charge to it. It's just an uncharged molecule. Okay, but let's say we bring it towards this region of electron density. What's going to happen is we take the electron from the carbon and it goes towards the bromine. Okay, so it's electron, and what happens is as this gets closer, it has a slightly positively charged, and this is a slight negative charge. The reason for that is because the electrons get pushed towards this bromine because repulsion, right? Would you agree that in this bromine bond, if I write it out like this is essentially two electrons, a shared pair of electrons that are moving around in this bond, and as it gets closer to this region, this high region of electron density, you're going to have the electrons pushed to this end, right? Because electrons repel electrons. As it does that, this now becomes slightly negatively charged, delta. This is a delta size, slightly negative, and this becomes slightly positively charged. And thus, the electrons get attracted to this bromine. Yeah. And what happens? You then get this. And also what happens here is, because this is now delta negative, this means that it has the tendency to draw the electrons towards itself. The electrons go towards the bromine. Okay. And what do we have here? We now get this C, H, 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 Br. That's the H, and then we've got the Br that's now bonded here. Okay. What's happened here now is we now get this overall positive charge. Why do we have an overall positive charge? Because we've lost electrons from this bond, and the electrons are now here. So overall, this carbon is now it's missing an electron. Yeah, because the electron's gone here. If you lose an electron, it's now positive charge. Okay. Right. Then what happens is we've got this Br. Do you remember this Br that was here? This is negatively charged. This will have the two electrons that came from this bond, and this negative gets attracted to positive. And finally, we end up with our C, H, 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 Br, and Br. Okay, so this is how an alkene can turn into a bromoalkane. Okay, now this is a very complicated mechanism. Again, this is A-level stuff, year 12. I only did this just so you can kind of see how this happens. Otherwise, when you get told this at school, you just take it for granted. Okay, and remember, here we try to get you ahead of the class. So you want to know this. If you can kind of see what's happening, don't worry about getting all these, like in A-level, you'd have to get this perfect. You'd need to get this arrow exact, a curly arrow like this. This needs to be a curly arrow. This needs to be the correct charges, all of that. That needs to be perfect for A-level. But for GCSE, if you can just kind of understand what's going on, that this negative charge that's in the double bond kind of attracts the bromine, and then causes this shift in charge in this bromine molecule, and thus causes one bromine to attach to this carbon, leaves an overall positive charge, and allows the other bromine to then, the bromide ion gets attracted and forms this bromoalkane. Yeah, as long as you kind of understand what's going on, don't worry about memorizing this, it's just for understanding. Okay, so when we said that the carbon-carbon double bond breaks, hopefully you see why it breaks. It breaks to be able to join this bromine. And then we said that it turns the bromine water colorless. Why does it do so? Because the bromine's been added across the double bond. That's what we say. It's been added across the double bond. There's no bromine in solution, therefore it's not going to be orange anymore. Yeah, because bromine in solution is orange brown in color. Okay. Would a hexene being tested using bromine water called 1,2-dibromohexene? Well, it depends where the bromine is added. So for you, because you've mentioned this, if we use hexene, Hexene is 6, 3, 4, and let's just say 5, and let's say the double bond's here, okay, 6. Technically, this double bond can break and the bromine can be added here. Okay, in that case, it's 1, 2, 3, so it is it'll be 3, 4 dibromohexane. Okay, if, however, and again, this is all nomenclature stuff, you'll learn this in A-level anyway, so don't worry don't get bogged down on this. But if, however, the double bond was, let's say, here, then yes, the bromine will be attached to here and you'll get your 1, 2 dibromohexane. Yeah, I just want to correct you. You said hexene, you want to make that hexane. Okay. Someone's saying delta negative. So do you remember I talked about in one of the previous lessons, I talked a little bit, very briefly about electronegativity, especially when we looked at the, Van der Waals forces, London forces. We talked about inducing an dipole. There was a transient induction of a dipole on a neighboring molecule, and I said delta negative means small negative charge. It's a partial charge. Yeah, it's not a complete ion. It's not fully negative. It's just slightly, meaning that the electrons at that point in time are more to this side of the bond. So if we use this, the electrons, can you see? Usually when we take a bond, we expect the electrons to be just somewhere in the middle, so that way neither end is more negative. But electrons don't work like that. They just move around randomly in the bond, and so sometimes they'll be over here, sometimes they'll be over here. So it's that. But the reason why they're over here is because this negative charge from this double bond is pushing the electrons to the other side. Yeah, it's literally repulsion. Okay, cool. Anyway, I'm not going to spend any longer on this. This is just for understanding. Don't worry about like memorizing any of this or knowing how to draw this mechanism. But those of you that do chemistry at A-level, which I'm sure a lot of you here will be doing, you've got your early insight into that. So when you do, by the time you get to, you'll probably forget all of this, but at least you would have some familiarity to it. Okay. So hydrocarbons are good fuels, the main source being crude oil. And crude oil is found in rocks. Now, crude oil is made from animals that died millions of years ago. You then take heat and pressure to turn them into crude oil and natural gas. Hence, they're called fossil fuels. It's coming from the fossils of animals that died millions of years ago, right? Now, fossil fuels are a finite and unsustainable fuel source. Other natural sources of hydrocarbons will be coal, charcoal, and wood. Okay. Right. This is very important. Let me see if there's any other questions. What A-level? So I did biology, chemistry, maths, physics. Types of questions. So what? Oh, okay, this is a very good. What types of questions could they ask about bromination? So they could ask, give the test for an alkene. Yeah, very simple. And you would say add bromine water, and if an alkene is present, it will turn from orange to colorless. Okay. What else could they ask about bromination? They could very much say, this is more feasible. This is more likely than what I just did. They could say, give an equation for the reaction of ethane with bromine, and you'd have to say that it forms bromoethane, basically. Yeah, you'd have to write out the equation. Or they may ask you to write out the displayed formula. So the displayed formula would be this. They could say bromine water was added to ethene. Give the displayed formula of the product, and the product would be CC. Will be this. It will be what I just wrote here. This is the displayed formula.